So hey everyone, with some feedback from the previous video which was entirely upon attention modules and transformer. I thought it got a bit more advanced, so this particular playlist will be covering the basics of DL just to get an intuition and idea of it. Again, it won't be entirely basic. You should have some previous knowledge about, like a bit of knowledge about DL and an overview idea of how DL works, and you'll be good to go. So in this particular playlist we'll be covering mostly three topics in detail. The first one is activation function, the second one is the loss function, and the third one is backpropagation. So first two videos they'll be mostly theoretical. The last, backpropagation, we'll try to implement it from scratch using NumPy. And yeah, that's pretty much it, and that will cover the entire DL and some of the concepts. Again, we'll try to figure out some of the menu details which other videos and other content miss it out. So we'll try to go through them and try to see how those things works the way it works. So let's start with the first topic of the day, that is the activation functions. So let's start with the pretty basic definition of functions. So what are functions? So basic definition, a function is a mapping for an input with an output. So f of x is equal to y, x is your input, and the function takes that input and maps it to a certain output, that is a y. So f becomes a function. Now there are many categorization of functions which we won't go into that basic mathematics stuff. But what was the need of an activation function? We'll see why do we needed activation functions in the neural networks. I mean, it was working fine before activation functions, so what was the need for it? The second one is conditions. So not all and every functions can be called an activation function. There are certain rules which a function should follow in order to be called as an activation function. So we'll see why those rules and what are those rules. Like, this is also good questions that if there is a rule written, why is that particular rule and how it is intuitively coming out from that particular thing. So we'll see why those rules are there and what are the implications of those rules. So we'll start with basics and we'll start with perceptron. So perceptron, basically a neuron. So again, I'm assuming that there is a certain level of knowledge of deep learning and neural network over here. So we'll start with the neurons. So this is your basic neuron. It takes an input, let's say x, a vector x, and then it produces an output, vector y, or it can be a scalar also, not an issue. So the first neuron was empty neuron, like Macaulay-Putz neuron. So if you see this particular neuron over here, so this is a cell, call it a cell, and then this is your activation functions. This is your f. So what is happening over here? So you have a input vector x. This input vector is x1, x2 up to xt. So this is a d cross one dimensional input vector. So you are giving it there, and then you have certain weights associated with each of this particular. So it's a matrix, the weight matrix. Let's say r t cross n, assuming anything. So this weight matrix, what is doing? So w1 into x1, w2, so individual weights are getting multiplied, and then we have a bias w0. So it's multiplying them, summing them up, and adding a bias, and then this value, whatever it's come out to be, we call it a. This is your activation value. And on activation value a, we apply a function f. So when you apply a function f, this is your activation function, this is your activation value, and you get an output h. This is called an activation output. So basic stuff. This is how MP neurons work. So what was the need for this? So before going into the needs, let's understand a basic neural network architecture. So neural network, you have an x1, x2 up to xt, and then next layer, let's say this is these are 1, 2 up to h number of neurons, then again a next layer, these are again 1, 2 up to, let's say, k number of neurons, and then your final output layer, this is 1, 2, and let's say m number of neurons. So each of these particular neuron is connected with every other neuron in the next layer. So this is why it's called the fully connected neural network. So this is your typical architecture. This is how it works, and then each of this will produce an output, and then you can apply loss function and then propagate over here, tune your matrix accordingly, and it works fine. So this is the basic structure of a neural network. So like there are two types of networks now, a deep neural network and a non-deep. So deep and non-deep, they basically means number of hidden layers. So if I increase the hidden layer from 1 to 2, 3 and 4, so it becomes a deep neural network, whereas if I have a single hidden layer, it becomes a non-deep neural network. Basic definition, nothing interesting over here. So FCNN, fully connected neural nets. Fully connected neural nets. Now, if you want to take an analogy, it's equal to the mesh topology. Mesh topology. So, like what happens over there, that NC2. So everything is connected over there. So that's how it goes by the name mesh topology. Now let's get through a basic. Before understanding, we'll come to this slide later. So let's start with the activation functions for now. So just now in the MP neuron, we saw that we have some input. We sum over wi xi, we add a bias, and this becomes our activation value A. Activation value A will be a vector. Now after getting this vector, we apply an activation functions on A, and this become our activation output. Cool. So we have to worry about this particular function f for now. So let's start with the need. So if you see this multiplication wi xi plus w naught, this is linear in nature. This is linear in nature. So what do I mean by linear in nature? Linear in nature, that it's a linear transformation. So like rotation. So you take something, you rotate it something with some angle, that's become your linear transformation. So this basically matrix multiplication, it's a linear transformation. So linear functions, they have to follow certain properties in order to be a function, to be said as a linear function, but we'll go with the basic one. So if a function is a linear, so f of cu plus f of cu plus v, this should be equal to c times f of u plus f of v. If f is a linear function, it should satisfy this particular equation, and matrix multiplication does satisfy, so it is called a linear function. So what was the need of bringing activation function into picture if this particular summation was working fine, wi xi plus w naught, like the matrix multiplication transformation, it was working fine. So why was there a need to introduce another function of activation function? Now if you see, we'll just go quickly through it. These are certain data points I'm having. Consider a 2-class data point, and now if I have a class, let's say this one, I want to categorize it like whether it belong to this sector or to this sector. So if you see our existing data, it has a line distinguishing between them. So a line differentiate these two data points, and the perceptron convergence theorem, it says that if your data is linearly separable, so perceptron will always be able to find this equation of this particular line in a finite number of steps. So this is the convergence theorem of the perceptron, and it's verified with multiple resources as well. But the issue was, what if your data is not linearly separable? I mean, data distributions, whatever model we are predicting, they follow very complex distributions like images, faces. They are not linearly separable in a certain way. But that was the issue with this particular transformation. So in a certain way, it doesn't mean how many times I apply this particular function, matrix multiplication with different matrix multiplication. Application of linear functions on a linear function is again linear. So there was no way in which you can fit a particular non-linear shape into your distribution to distinguish between two classes. So suppose if your data was something like circular, so these were my data points, and these were my data points. So there is no line that distinguishes between these 2 points and these 2 points. So in this case, MP neuron will fail to give you accurate result. For this, we need a certain function that could produce this particular separation boundary, and this is where we need non-linearity. So that was the need for introduction of a activation function over here, that is to introduce non-linearity. This was the main reason. Now in which cases, what properties a function should follow, so that we can say that it is exactly activation function. The first one is non-linearity, obviously that's the basic need for the thing. The second one is continuability and differentiability. Now continuity, so continuous and differentiable function. Continuous and differentiable function. So if a function is continuous, it can be differentiable or it cannot be differentiable, but if a function is differentiable, it has to be continuous. Basic property of functions. So now why these properties, like we understood why non-linearity is required. Now why continuity and differentiability is required? So if you see, when we try to update the rules, I mean, how do I put it? So this is your neuron. Where was that? This is your fully connected neuron. So what happens here, you get some output, like you get some output from here, and then we take derivative with respect to input. I mean, with respect to input, I mean with respect to each of the previous layer, and that derivative flows backward, like gradient descent algorithm. Theta nu is equal to theta old minus eta del theta. So gradient descent algorithm. So for calculation, for possibility, like the gradient should be able to flow properly backward, and that is why we need a differentiable function over here, so that this differentiation doesn't cause an issue in the updation of the new parameters. So that's the reason with differentiability. Like again, you'll get more clear with the differentiability part once we try to implement backpropagation, and it will be much more clear over there. Now these two properties, these are the like required one. The optimal but not important are monotonic, smoothness, and maybe saturating or non-saturating. So monotonic means that this is a monotonic function. So if a value, so if I have 2 points x1 comma x2, so if x1 is less than x2, so f of x1 should also be less than f of x2. So this is the property of monotonicity, that it grows in a certain way. It doesn't like if you see this function, this is actually an activation function, but this is not monotonic in this particular sector. So but still it's I guess Silu, yeah, Silu maybe, Silu or Gilu. So this is actually activation function, but it's not monotonic. So that's why I've written that it's optimal property. Like it is it's good if you have it, but it's not important for having the function to be called as activation function. Saturating and non-saturating. So saturating means reaching to a point. So by saturating means if there's a function f and x, so if I take x to the infinity, it reaches to certain value a. So this is your saturating function. It goes to infinity or x goes to minus infinity. So if I say a saturating function, so this one, this sigmoidal is sorry, this sigmoidal activation function. This is sigmoidal activation function. This is saturating at this particular point. So if we'll come to it, if this is logistic sigmoidal, then this is 1, and if it is again, if it is this is 1 and then this is 0 if it is logistic sigmoidal. If it is tan h, so this will become 1 and this will become minus 1. So going up to infinity, it reaches a certain point. So that is your saturating function. If you take a non-saturating function, so non-saturating function is ReLU. So the graph of ReLU is basically y is equal to x for x greater than 0. So it never saturates. If you keep on increasing x, y will keep on increasing, doesn't read a particular value. So that's how it goes. So these are like optimal but not important. So you have saturating or non-saturating functions over there. Then let's come to common activation functions. Like we haven't discussed neural networks, we haven't discussed how these activation functions are applied. We have discussed that what are activation functions, what are its need. So we'll just go through some of the common activation functions, and similarly in the next video we'll go through the loss function, and then in the final video when we'll start backpropagation algorithm, we'll come to understand how those all relates with each other. So this last video will be important for the time being. Now let's come up to common activation functions, and we'll see to verify like it follows all those properties which I have mentioned above. Now sigmoidal activation function. So sigmoidal activation functions, by this word itself you can assume that it follows something S-shaped property. So this is your sigmoidal activation function. Now sigmoidal activation functions are like mostly there of two. There are two sigmoidal functions. One is the logistic function and other is the hyperbolic tan h function, or simply tan h. Now this is the formula. So f of a is equal to 1 upon this basic formula. So we don't need to remember it, but it's good if you remember it. So 1 upon 1 plus e raised to power minus beta a, and this is your curve of the sigmoidal activation functions. Now this is the saturating function. If x goes to infinity, it saturates at 1. If x goes to minus infinity, it saturates at 0. So this is a saturating function. It is continuous, it is differentiable. Is it monotonic? I guess so. It is a monotonic function. So this is the differentiation. So this will be used when we'll try to implement backpropagation. So this is the differentiation of f of x. So I guess it's pretty simple. So you can go with it. Then again f of a is equal to tan hx. Then this is again f of a, and this is a differentiation. So this differentiation part, they will be very important when we'll try to implement backpropagation algorithm. Then these set of functions, leaky ReLU, ReLU, parametric ReLU, and ELU, these are something important. Like currently ReLU is you can say is the state of the art everywhere in all the CNNs, convolution neural networks. ReLU is used mostly. So we'll see how, and we'll go through some other advanced activation functions for now. So ReLU is basically f of x. So x if x is greater than 0 or it's 0 otherwise. Now if you draw the curve of ReLU, so for all this section where x is less than 0, it becomes 0. From here it start increasing. So is this a linear function or a non-linear function? So if you see particularly this part is linear for him. So if I just include this part, so this will be a linear function, so it won't be called as an activation function, because non-linearity is a required condition for activation function. So this is how ReLU differentiates it. Now it is differentiable or not. So if you see this particular point at 0, it's not differentiable, because if you see another example, if I give the graph of mod x, so mod x is not differentiable at x is equal to 0. So a pretty neat trick for defining differentiability is that wherever you have sharp corners, there's a very high chance, or you can say by almost certainty, that this particular function will not be differentiable at this particular point. So wherever there is a peak or a sharpness in corners, so at that point the function generally doesn't get to be differentiable. So that's what happens with leaky ReLU and ReLU. So the implementation of ReLU is as such that we define this particular point, and thus we try to overcome the non-differentiability. Like wherever you get x this is particularly defined, this is fixed. We're not calculating this, it is totally independent. So we are not calculating anything, it simply becomes 0. So while back propagating, this part doesn't cause an issue, because this part, as soon as we get f of x less than 0, we simply put it 0. It doesn't try to differentiate itself. So that's how it tries to overcome its required property of differentiability. Now leaky ReLU by term, it means that it allows some of the gradient to flow through it. So it becomes something like this. So this particular part is negative. It allows the flow of certain gradient along it for x is less than 0. So it leaks some gradient, and hence the name leaky ReLU. Then parametric ReLU, you can say this particular okay, so if I do this, f of x is equal to x for x greater than 0 or 1.5, and it's 1.5. So this becomes your leaky ReLU. Now if I do this, f of x is equal to x greater than 0 or some beta x for x less than 0. So this beta is again a parameter, so it depends on your x, like this is parameterized, so it becomes parametric ReLU. It's not fixed like this particular value. This is just an example to get through it. And then ELU is again exponential linear unit, so it becomes simply e raised power x. So that's how it goes. Now these are the two of the advanced activation functions which are used, that is the CELU and the GELU. So let's start with CELU and GELU. So the derivation of CELU and GELU, it comes from the ReLU itself. Now if you go through the definition of ReLU once again, now again this derivation is not that trivial. So x for x greater than 0, 0 otherwise. Now this could be rewritten as 1.x into 0.x. Makes sense? No difference in anything. The function works exactly the same, but there is a certain thing. Now as soon as you see this, you can say it in a certain way that it takes x with the probability 1 when x is greater than 0. Otherwise it takes x with the probability 0. Now as this 1 0 comes, there is a distribution which follows certain point of thing, the same behavior it follows, which is a Bernoulli distribution. Now Bernoulli, if you see Bernoulli of x comma p, so it is p raised power x 1 minus p raised power 1 minus x. This is your PDF of Bernoulli distribution. So this was somewhat makes sense with that. Now again, one of the intuition that follows the activation functions of CELU and GELU is the dropout. So dropout we haven't I mean, if you have done it, so what it does, it with certain probability it activates the neuron, and with 1 minus p of that probability it deactivates the neuron. So basic definition of dropout. So with the probability p it takes x, and with probability 1 minus p it takes 0. So again you can write it like this. Exact same definition, just the only thing is that here it is doing with a certain probability of p. Now it makes sense to combine these two. So what I can do is f of x is equal to m of x. Now m, here m was 1, here m was taking 1 with certain probability p, so m could be coming from a Bernoulli distribution. Bernoulli distribution of what? A function of x. So m is coming from a Bernoulli distribution, which is again a function of x. Now this phi, it could be anything. It could be sigmoidal, whatever function you want, sigmoidal, anyone. But generally people tend to choose this phi as normal distribution. Now there is no hard and fast way of saying that why it's done. It's just you can say convenient way of doing it, so people go with that. One thing could be because of central limit theorem, that most of the distribution, if you increase the data set, it tends to move toward the Gaussian distribution, normal distribution. So maybe that would be a great, I mean, that would be a better explanation of why phi x was chosen to be a normal distribution. But yeah, sigmoidal also does the same thing. I mean, it does pretty much the same thing, no difference at all. But we'll go with the normal distribution. Now, so our fx becomes m of x. Now let's see how the definition of this particular CLU comes. Let's take the expected value of f of x. It comes out to be expected value of mx, and this could be written as so m is coming from Bernoulli distribution. So now since this phi x is a probability, so phi x need to lie between 1 and 0. Make sense? Now since m is coming from a Bernoulli distribution which takes a probability of phi of x, so with probability phi of x it takes 1 into x. With the probability 1 minus phi of x, it takes 0 into x. So this is what the expected value. So this simply turns out to be phi of x into x. Now what is this phi of x? Phi of x is basically probability of x is less than or equal to x. Make sense? So this is basically the PDF of distribution, PDF of normal distribution. So this is where it's the definition of KLU is coming into picture. So KLU of x will simply become probability of x into less than x, which is basically the sorry, not PDF. I'm sorry, this is cumulative distribution function, CDF. This is CDF of x. And now what happens is that this becomes CDF, and then this is simply x of phi of x. And now this CDF could be approximated. We can use certain approximation to calculate out this CDF, and then that forms the definition of KLU. So after doing certain approximation, if you see this particular x cube terms, one of the disadvantages of KLU was this particular x cube itself. So x cube provide you instability. So if you work with mobile devices, you can find that x works in floating points number, because all these x and vectors, they are basically float 32 or float 64, these type of data types. So if you take a very small value and then you cube it out, so it provides very much instability when you're working on mobile devices. So this was one of the drawback, like not drawback, but yeah, it was one of the issue with the KLU. So KLU can again be approximated by using x of sigmoid of 1.702x, what's written over here. So this entire summation and everything could be approximated by using x of sigmoid of 1.702x. The graph, if you plot of this function and this particular function, they tends out to be exactly very similar. So this is the approximation we use in PyTorch while calculation of KLU. So that is Gaussian error linear unit. Now come out to be sigmoidal linear unit. Sigmoidal linear unit is basically same thing, just it becomes x of sigma of x. So we are not using this 1.702 parameter. So this is much more about this particular kind of activation functions. And now I think there was a paper of Google itself which tried to train a neural network that could estimate activation functions for you. Like you don't need to define that, okay, use ReLU, use sigmoid, use it. It can find a certain class of activation functions that best fit your model. So they're not citing those paper right now, but the main result was that all those functions which follows properties like this, m of x, where m is some phi of, let's not take phi, let's say theta of x into x. These type of functions which follows this particular structure, they turns out to be better activation functions. So this was the result of that particular paper. So this is the plot. This is basically take any random value and then you can plot it all those functions by using those parameters. So this is your ReLU, then leaky ReLU, then parametric ReLU, and then ELU, exponential linear event. So all in every of those ReLU above x, it's the same thing. Take x if x is greater than 0. Otherwise there are certain changes which tend to be like changing that. You can take parameter, you can take that as a hyperparameter, that what should be the flow of the gradient backward, which is doing best. And then this is again CLU and GLU, so the same thing. So this is again this function is not monotonic over this particular range of point. So again this is again monotonicity, as we discussed above, that monotonicity is a desirable property but it's not required. Now the last activation function is which is very much popular, is softmax. This about this softmax we discussed its uses in that particular softmax and cross attention and self attention video. Now softmax is pretty much simple. It basically squashes your outputs into a probability distribution of 0 to 1. So this will be 1, then this will be 0. So like generally we tend to use in the last layer, so that suppose if you're trying to distinguish between 10 classes, you have let's not say 4 classes. So you want these classes to output a probability, that by what probability this particular class, I can say that this data point belong to this particular class, or this particular class, or this particular class, or this particular class. So in the last layer we use softmax, so that the output of whatever it's coming out, it's summed over 1. So if this is 0.2, this is 0.6, this is 0.1, so 62819, this will become 0.1. So this is why softmax is used. So softmax is again simple function, where if you have a vector, let's say 3, 4, 5, 6. So what you do, if you calculate softmax, so it will again be a same vector. Let's say A, B, C, D, same dimensional vector, where A will be equal to e raised power 3 divided by e raised power 3 plus e raised power 4 plus e raised power 5 plus e raised power 6. Similarly, B will become e raised power 4 divided by 3 plus e raised power 4 plus e raised power 5 plus e raised power 6. And similarly, C and D will come out to be the same thing. So this is how and why we use softmax. Now this is pretty much a basic introduction of activation functions. There are tons of activation functions and research going on there, which try to find out more and more complex activation functions that can better train your model. So we'll try to figure out those details if we get time into another video of advanced activation functions. I hope like a basic concept and basic grasp of this activation functions, their particular required properties, the necessary condition, and one thing that remains is the derivability property, that why the activation function should be differentiable. So it will get more clear once we implement backpropagation. So till then we'll try to see what else we can do. The next video will be on loss function, and like it's really important, it kind of take two videos to discuss every loss functions, and it's one of the most important topics in deep learning and neural nets, because loss functions keep on updating, like we keep on updating loss functions. Activation functions tend to be more or less the pretty same, whatever research have been done, but loss functions are like they keep on updating on a daily basis. So we'll go through that, and after that we'll try to implement backpropagation.